This video will cover the use of alcohols as nucleophiles and electrophiles. Alcohols are particularly useful synthetically because they can act as both nucleophiles and electrophiles. First, let's look at how alcohols can be used as nucleophiles. Alcohols in an unmodified state tend to be weak nucleophiles. This means that they typically require a very strong electrophile when in their protonated state. An example of this is the alkoxymercuration-demercuration reaction. In this reaction, our nucleophile is the protonated alcohol. The electrophile in this reaction is the mercury intermediate. This mercuric intermediate is a very strong electrophile because it's positively charged and because it has a very strained ring. This type of very strong electrophile is required to react with the protonated alcohol, which is a weak nucleophile. Deprotonation of an alcohol to make an alkoxide makes the alcohol a stronger nucleophile. These stronger nucleophiles can react with weaker electrophiles, meaning that the type of reaction they can react in is much broader. Remember that there are two ways to synthesize an alkoxide ion. In the first, we treat the alcohol with sodium or potassium metal. This redox reaction produces the alkoxide ion and hydrogen gas. The second method of producing an alkoxide ion that we have discussed is treatment of the alcohol with sodium hydride. Hydride is a strong base that is capable of deprotonating the alcohol, again to synthesize the alkoxide ion and hydrogen gas. Next, let's look at the use of alcohols as electrophiles. Just as we saw with the nucleophilic examples, an unmodified alcohol is a weak electrophile. This is because an unmodified alcohol requires the leaving group to be hydroxide ion, which we know is a poor leaving group. When we react an alcohol with a nucleophile, it produces the substituted product along with hydroxide, which we know to be a poor leaving group. In order to make an alcohol a better electrophile, one way we can do this is by protonating the alcohol, producing a good leaving group. Protonation of an alcohol produces water as a leaving group, which is a good leaving group because it's neutral. However, protonation typically requires a strong acid, and many nucleophiles are basic as well as being nucleophiles, and protonation makes them much weaker nucleophiles. For example, the following nucleophiles are not compatible with an acidic solution. These include Grignard reagents, organolithium reagents, acetylide ions, and alkoxide ions. These nucleophiles and many others won't survive an acidic environment required to make an alcohol a better electrophile. Therefore, organic chemists have come up with other ways to make alcohols into good electrophiles. The most common strategy for making an alcohol into a better electrophile use something called a tosylate ester. Tosylate esters make an alcohol into a better electrophile without the use of acid, which could quench a good nucleophile. A tosylate ester replaces the proton that's typically found on an alcohol. This is the tosylate group. Tosylate is often abbreviated using TS. In replacing the proton with the tosylate ester, we turn a poor leaving group, hydroxide ion, into a very good leaving group. Looking at the structure of the tosylate ester, you can probably guess why this is such a great leaving group. Tosylate esters are really good leaving groups due to resonance. The anion that is formed with this leaving group can access many resonance structures, helping to stabilize it. Tosylate esters can be synthesized through an SN2-like reaction of an alcohol with tosylate chloride. The alcohol is treated with tosyl chloride in the presence of a bulky, non-nucleophilic base, such as pyridine. The product of this reaction is the tosylate ester. The mechanism involves attack of the alcohol on sulfur, kicking off the chloride ion. Next, the alcohol is deprotonated by the pyridine to produce the tosylate ester. Because the tosylate group is large and takes some time to draw, chemists typically abbreviate this reaction. The alcohol is treated with tosyl chloride, which is given the abbreviation TSCl, and the base pyridine to give the tosylate ester, which is often abbreviated like this. Because the tosyl group is such a good leaving group, tosylate esters make very good electrophiles in both substitution reactions and elimination reactions. Tosylate esters can be used in many different types of substitution reactions. Typically, they undergo SN2 reactions. Remember that SN2 reactions require strong nucleophiles. These strong nucleophiles include the hydroxide ion, which synthesizes an alcohol, the cyanide ion, which synthesizes a nitrile, a halide, which synthesizes an alkyl halide, an alkoxide ion, which synthesizes an ether, or an amine, which synthesizes a quaternary amine. All of these reactions occur through an SN2-like mechanism, where the nucleophile attacks the carbon as electrophile, kicking off the tosylate group. Tosylate esters can also function in elimination reactions, where a strong base can remove the proton on a carbon next to the tosylate group, forming the double bond and kicking off the tosylate leaving group to produce the alkene product. There is one more thing to consider when comparing alcohols acting as nucleophiles versus electrophiles. And this is the fact that a different bond breaks in the alcohol depending on whether that alcohol is acting as a nucleophile or an electrophile. If we consider the structure of an alcohol, if that alcohol acts as an electrophile, it is the bond between the carbon and the oxygen that is breaking. However, if the alcohol is acting as a nucleophile, it is the bond between oxygen and hydrogen that breaks. This is important when the alcohol is a chiral molecule, particularly when it's chiral at the alcohol center, because if the bond between carbon and oxygen breaks, that changes the stereochemistry. However, if the alcohol is acting as a nucleophile, the bond to carbon isn't breaking, and therefore stereochemistry is retained when the alcohol is the nucleophile. Now, let's look at an example. Let's consider the synthesis of an ether using the same alcohol. We will perform two ether syntheses with this alcohol, one with this alcohol acting as the nucleophile, and one acting with this alcohol as the electrophile. This will have important consequences on the stereochemistry of the product. If our alcohol is acting as the nucleophile, it is the bond between its oxygen and its hydrogen that is breaking. Therefore, the stereochemistry at the alcohol center should be retained. In order to use this alcohol as a nucleophile, we first have to deprotonate it. To do so, we can use sodium metal. This produces the alkoxide ion, which can then be reacted with an electrophile, such as an alkyl halide, to produce an ether. The product is an ether that retains the original stereochemistry and our starting alcohol. However, if we make the same ether using the same starting alcohol, but we use that starting alcohol as the electrophile in the reaction, in order to turn this alcohol into a reasonable electrophile, we can react it with tosyl chloride to produce the tosylate ester. We can then react this tosylate ester with a good nucleophile, such as the alkoxide ion. Because our original starting alcohol is acting as the electrophile in an SN2 reaction, we will see inversion of the stereocenter. Therefore, it is important to consider stereochemistry of the products when we decide whether we want to use an alcohol as a nucleophile or an electrophile.